This is 2.5. And this topic is limits at infinity. So maybe let's start with me explaining the difference between the previous topic and infinite limits and limits at infinity. So in the previous topic we had a limit with x approaching a number, right? So number c, and then we had a function, and that was positive infinity or negative infinity, right? So yeah, so basically let me give you an example, right? So limit with x approaching 2 with 1 over x minus 2. Okay, so let's say we're approaching that 2 from the right. Okay, so if that happens, maybe let me graph it quickly. Okay, so we'll have that vertical asymptote at 2, and then the graph will look something like this. Right? So there is the right branch, here's the left branch. Okay, so you see that if I approach the x from the right side, right, approach 2 from the right side, right, so my x's are going this way, then the y's are going this way, so the answer is infinity, right? So that's where that infinity is, right? So x is approaching a number, and y's or values of the function are going to infinity, right? So that is infinite limits. So limits at infinity, that means the difference is that x approaches infinity. Okay, so there's like a line that separates those two. Okay, so let me show you the simplest limit at infinity. So limit with x approaching infinity. I mean simplest, right? Like the basic one, 1 over x. Okay, so we see that if those x's are getting bigger and bigger, then the whole thing, right? So I'm dividing 1 by increasingly larger numbers, then the answer is 0, right? 1 over very large number is very close to 0, so limit would be 0. And similarly, if I had limit with x approaching infinity of 1 over x squared, right, I also get 0. All right. Yeah, so that's the difference. And let's start with what should we do? Let's start maybe with the definition of a horizontal asymptote. Let's do that first. So horizontal asymptote. Okay. And yeah, before I give you the definition, let me maybe remind you the definition of the vertical asymptote. So it went something like this, right? If there was a limit with x approaching a number, of some function, and if that limit is infinity, then this equation x equals c is a vertical asymptote, right? So that's that vertical asymptote, right? So we had, let me show it to you here. Okay, so here we have so here we have x approaches a number, x is approaching 2. From the left, could be from the left, could be from the right. It doesn't matter, right? So yeah, as I just showed you, right? So if x's are getting closer and closer to to that 2 from the left in this case, then y's are going to negative infinity, right? So this could be negative infinity here. It doesn't matter. Then that x equals c, right? So x equals 2. So this vertical line is x equals 2. And is that vertical asymptote. Okay, so that's a vertical asymptote. So let me maybe emphasize that here. Vertical asymptote. Vertical. This spells vertical. Asymptote. Alright, so that's the definition of the vertical asymptote. Alright, so that's the vertical. So let's look at that horizontal. Okay, so the definition goes like this. So definition. So if f of x, it's pretty long. But sometimes, yeah, it's good to, to see and read and hear that. Let me pause it for, there's this noise. Okay, let me actually write the definition in a different way. So I'll erase that. So let's write it this way. So if limit with x approaching infinity of f of x equals some number L, then the line y equals L is a horizontal asymptote. Oh, yeah, it's a horizontal asymptote. Of f of x or f. Okay, I think the easiest way to explain this definition would be to give you an example. So example 1. Okay, so let's look at something like this. So f of x equals 3x squared over x squared plus 1. And I think maybe the best way to illustrate this idea of horizontal asymptote would be to graph it. Okay, so 1, 2, 3, 4, and yeah, I'm just gonna, draw that horizontal asymptote, and then the graph would look like this. Okay, so yeah, so I hope you understand this, right? This definition. So basically, right? So if x's are approaching infinity, right? So I'm going with my x's are just going this way, right, or that way. Could be positive infinity, could be negative infinity, and then the y's, right? The value of y are approaching a certain number, right? The number is 3. Then the line y equals that number, y equals 3 in this case, is that horizontal asymptote. Right, so one more time, x's are approaching infinity, right? So if we took a limit, so limit with x approaching infinity, so 3x squared over x squared plus 1. Right, so that limit equals equals 3. And I'll show you an algebraic way to figure it out. So we could have, right, a positive infinity, and we could have the negative infinity, so negative infinity, and that also will be 3. So 3x squared divided by x squared plus 1, and that limit is also 3. So let me maybe quickly explain, just to give you intuition of what's happening. Right, so if x's are approaching infinity, right, so we're here. So, right, so when the numbers are really big, that 1, that plus 1, doesn't really matter. Right, so we could even maybe just ignore that 1. Right, so I'm doing limit of with x approaching infinity of 3x squared over x squared. Right, so as I said before, and when numbers get really big, that 1, that plus 1, and we can ignore it, it doesn't really matter. And then, so in this case, when I'm here, right, so those x squares cancel out, and we just simply have 3. Okay, so that's kind of the intuition, the idea behind it. And in a moment, I'll show you how we can solve it algebraically. Okay, so let's open the next page. And yeah, let's do a couple of problems. So example 2. So find the limit. And we have a, so let's look at the limit with x approaching infinity, 2x plus 5. This is 5 divided by 3x squared plus 1. Okay, so that's the first one. Second one, x is approaching infinity. So this one is similar, but it has 2x squared on the top. Plus 5, 3x squared plus 1. And the last one, C, I have limit. And then this time I have 2x cubed plus 5, 3x squared plus 1. Yeah, so maybe we'll start with just thinking about it. So when you look at that first one, and you see that just like in the problem before, we can maybe ignore that 5. I mean, not maybe, but ignore that 5 and ignore that 1. Okay, because when the numbers are large, those two constants just don't really matter. And then what can we do, right? We could just kind of, if these two, right, those 5 and 1 are not there, then we can maybe cancel this x with this x. And again, we could keep that. Let's keep those 2 and 3. So I'll have 2 on the top and then 3x at the bottom. Right? So one more time, I ignore those two, right? Those two constants, because when numbers approach infinity, those two constants don't matter. And then if I don't have those, right, then I can cancel those two x's. Okay, and then I end up with 2 divided by 3x. So that, and remember when we had this there was basically, we could look at it like this, times 1 over x, right? So if x approaching infinity, this is 0. And anything times 0 is simply 0. Okay, so this is not really an algebraic way of solving it, but it's just kind of, we're just thinking about it. All right, so let's look at the second one. So the second one is similar, right? We can, again, right, we will ignore these two, 5 and 1, and then we can cancel those x squares, and if that happens, right, we end up with 2/3. Okay, so that's our prediction, and then we'll solve it algebraically in a moment. And yeah, looking at the last one, these two are gone, and then I would have, after I simplify it, I would get 2x over 3, or simply 2/3 times x. All right, so if I take increasingly, right, big numbers and plug into for x, I'll simply get infinity. Okay, so that's our prediction, and now let's solve it algebraically. And keep in mind, right, I showed you that a moment ago, right, that if I have a limit, x approaching infinity, and whether I have 1 over x, right, or 1 over x squared, both of them equal to 0. Okay, and I hope you understand, right? I'm plugging in big numbers in the denominator, so the whole thing just gets closer and closer to 0. Okay, so to solve the first one, I will do it here. That's why I have that limit. Infinity. What we can do, we can maybe, what is the best way? Maybe divide the top and the bottom by x squared. Okay, and there's many different ways, so let's do that. So if I divide the top by x squared, I get 2x divided by x squared, right? Plus 5 over x squared. And the bottom will be 3. X squared over x squared plus 1 over x squared. Okay, so I'm just gonna write that fraction. So I can cancel those x's. So I get 2 over x plus 5 over x squared. The bottom is 3. 1 over x squared, right? So this 0. So 3 plus 0. Okay, so let's look at it. So if x is approaching infinity, this is 0. This is also 0. Let me erase this part. Okay. So now 2 over x approaches 0. So it goes to 0. 5 over x squared goes to 0. Okay, so 0 over anything is 0. Okay, so our prediction was right. And we get 0. And we can use the same technique here at the bottom. Maybe let's actually do it some other way, or different algebraic technique. So instead of dividing everything by x squared, I will factor x squared out. So basically this is the same thing, it's just slightly different. So x approaching infinity, what I'll do, I'll factor x squared out. Maybe it's easier to understand. So if I do that, this will be 2. and this one will be 5 over x squared. Okay, the bottom, right, I do the same thing, factor x squared out, 3 plus 1 over x squared. Okay, so x squares cancel out, then this goes to 0, should be an arrow, this goes to 0, and I get 2 over 3. So again, our prediction was right. And now, let me erase this. So here in the last problem, we predicted that the answer is infinity. So let's use the same algebraic method we did before. So limit x approaching infinity, and I guess, yeah, we'll factor x squared out as well. So x squared. So we'll have 2. If I factor, we'll have 2x. And then here we'll have plus 5 over x. 5 over x squared. Okay, and the bottom, again, x squared out. So 3 plus 1 over x squared. Okay, so now this is going to 0, approaches 0. This approaches 0. This will cancel out, and we'll end up with limit infinity. What do we have? 2/3 times x. Okay, so yeah, it's just algebra. So this goes to 0, as you see. This goes to 0, cancels. So we have 2x on the top divided by 3, the same as this. Alright, so if we start plugging in larger and larger numbers in there, the whole thing goes to infinity. Okay. Okay, so let me give you a couple of problems to do. So practice. First one is limit with x approaching infinity. So x squared plus 2, x cubed minus 1. Yeah, so I'd like you to solve those algebraically. So just like the way I did it a moment ago. Okay, so number 2 is limit with x going to infinity. The top is the same, so x squared plus 2. And the bottom is x squared minus 1. So that's problem 2. Problem 3. Limit with x approaching negative infinity. And we have 5 over x minus x over 3. Okay, and problem number 4. It's a limit with x going to an arrow infinity. And then we have sine x over x. Okay, so 0, so these are the answers. 1, positive infinity, and here we have 0. Okay. I want to show you one more problem, one more example. This is example 3. And so find limits at infinity. And the function looks like this. 3x divided by square root of x squared plus 2. And again, right, we'll do it algebraically. So we have limit x going into infinity, positive infinity. And yeah, so on the top we have 3x. At the bottom we have that square root. And what I'll do, I'll factor the x squared out. Alright, so I have x squared. And then I have 1 plus 2 over x squared. Okay, so if x is going to infinity, this goes to 0. So I get, I'm not going to write that limit, right? That limit should be here, should be there. But let's just not write it there, just to save time. So 3x, and here I have x squared times 1, right? So that's gonna be square root of x squared. Okay. Make this a little shorter. Square root of x squared is just x. So we get 3x over x, and that is 3. Okay, so if x approaches infinity, then the limit is equal to 3.